Greetings and welcome to a new video about DC series motor. In this example number 6, we will discuss a situation where we also use a switch to create an average terminal voltage. So let's look at an example. We have a DC series motor and it requires a terminal voltage of 60 volts to drive a constant load with a shaft speed of 125 radians per second. We know from this motor that the armature resistance is 400 milliohms and the field resistance is 200 milliohms, and we can neglect the rotational losses. The question A is calculate the required terminal voltage if the shaft speed is decreased to 100 radians per second. So we go from 125 to 100 radians per second. In the second case, we have the following situation. The required terminal voltage in A can be achieved by chopping the terminal voltage of 60 volts. So we create what we need in question A by chopping the terminal voltage of question of actually what they're given here in 60 volts. The problem now is what is then the required duty cycle given by D. Okay, let's look at our solutions and work this out step by step. Again, we start with a model of our DC series motor. This is our model, the terminal voltage again. We have the field winding part with the field resistor and also the field inductor, the armature resistor and also the armature inductor, and our back EMF. Now, in addition, we can say, well, then this is a series motor, so series DC motor, that the armature current is equal to the field current is equal to the terminal current. That's actually the condition we have here. Alright, so let's look at the required terminal voltage when we go from 125 radians per second to 100 radians per second for our shaft speed. Now we start with the terminal voltage equation. In this case we can use Kirchhoff voltage law and set up this equation. What we see is the voltage across these two nodes is equal to the voltage across each of these elements together. So the summation of this 5 voltages. So your voltage across this RF, voltage across this inductor LF, voltage across this RA, which is then the armature resistance, voltage across this inductor of the armature, and also the back EMF. That's actually shown here. We know that this is a DC system, so the reactances will be 0 for DC conditions. So we can then say that these two parameters will be 0. Then we have this situation, so that is then the reduced form, the simplified expression for our terminal voltage. Okay, that's the condition for the terminal voltage. Let's also look at the back EMF. Back EMF is given by this expression, motor constant times the shaft speed. Now we know also that the motor constant is a product of two constants, so actually two values. This is the K armature constant and also the flux, but the flux is then related to the field current by another constant K of F. Now if I now use also the condition that this is a series DC motor, then we can say that the armature current is equal to the field current, also equal to the terminal current. Now, using this condition in here, in the field, the flux equation, in the back EMF equation, then we can set up the equation for the back EMF in this form, where we see the armature current directly. Okay, that will be used later on, right? Going to the developed torque is given again in the similar form as the back EMF by the motor constant, but then times the armature current. If I again substitute the value for the flux here using Kf times If or Kf times Ia for the armature current, because these are equal to each other, then I have this expression. And that will of course be then Ki K times Kf and then times of course the armature current squared. Okay. What's next? Now, again, look into the terminal voltage. That's actually this expression. I can use in here the value here. Then I have this expression. Now if I now rewrite this a little bit such that the armature current is outside the parentheses, I have this expression. Now I can also equate this such that I have expressed the IA, which is then the armature current in terms of the rest of the parameters. The next step is substitute this in this formula for the developed torque. So that will then result in this. So actually use this expression for the armature current and substitute that in the expression for the developed torque. You will get this. What you see is actually a relationship which also has a square of the terminal voltage and also the square of this quantity here in the denominator of the current. Alright, what we of course want is the shaft speed for question A. So we need actually an expression for the shaft speed omega sub m. So we can go and then make an expression for omega sub m in terms of the rest of the parameters, which is actually, after doing several steps, you will get this expression. What you see here is then Vt, which is terminal voltages, over the square root of the product of the two constants and also the developed torque. But minus the sum of the two resistors, the armature resistors and also the field resistors, over the product of the two constants again. But in most cases, the armature and also the field resistance together will be very, very small. In this case, it is just 0.6 ohms together. So we can say this part of this equation is very small. So we can say that's probably very close to zero. Then this expression is very, very simple, that this actually is a relation in terms of just the terminal voltage and also the developed torque and the two constant in product form. Alright, again, continuing with our shaft speed here, what we can say is the following. If I know that the shaft speed is linearly related to the terminal voltage, I can say then this terminal voltage for the second case, a new case, over the terminal voltage in the original situation is equal to the ratio of the shaft speeds. That's just actually the condition which you get from here. So you can also write it down in this form, and you can say then, if I have an omega m2 of 100 radians per second and omega m1, which is 125 radians per second, and the associated, of course, the terminal voltage of 60 volts, I can then write this expression and I have then 48 volts. That is actually the answer to our question A. So we require a terminal voltage of 48 volts if you want to reduce the shaft speed from 125 radians per second to 100 radians per second. Looking again to the relation of the shaft speed as a function of terminal voltage and the rest of the parameters, because the shaft speed is linearly related to the terminal voltage. Alright, now let's move to the next step. The next step is the situation where we have the required voltage, but in this time we will do a chopping. Okay, how does this work? So the duty cycle is then the required value here. We will of course now apply here a voltage by using a switch which will then simulate the chopping. So the circuit looks like this. We have this switch here which will then has of course some duty cycle. The terminal voltage will be here, which will be again applied here as 60 volts, but the actual voltage across this two terminals, which will be actually the actual voltage will be applied to this system, again this is just a series DC motor, will be less because there is some switching time here, and that is actually the duty cycle. So some percentage of this terminal voltage will be on average be across this diode. What is the need of this diode? The diode is required in order to have a current flow while this switch is open. If I now look at the situation and I have a situation like this, that this actually the terminal voltage at this level, and I go down to 0, and again I go up and I go down, and I see in one period I have a situation that this is on So that means actually the switch is closed, so I will apply this VT, but there's also some percentage of the period that this is just open. So switch is open, so I don't apply any voltage here. Well, on average, I have of course a lower voltage than that applied terminal voltage here. So if I have this constant on, that means I just apply what we have here also here. Or constant off, that means actually I have 0 volts across these two elements. So we can just average what we have here by creating a specific duty cycle. Okay. Then the duty cycle is then given by this expression, which you see in the duty cycle expression is the time on over the period. So what is the total time that the switch is on, so actually closed, over the total period of this signal? And that is then related to the terminal voltage what we require over the terminal voltage actually what we apply across these two elements. So this is actually the terminal voltage we require on average. This is what we apply. So due to the switching, that will be of course lower than this. So the average voltage across this diode or across this series motor will be lower. And that is then just calculating this value will be 0.8. So it's 80% duty cycle. That means actually the following. In the complete period, our switch is for 80% closed and for 20% open. So for example, if this period is 1 millisecond, I will be on for 0.8 millisecond and I will be off, so I will be closed actually for 0.8 milliseconds. I will be open for 0.2 milliseconds. And on average, by averaging actually this signal, I will have then 80% of what I apply here. So if this is 60 volts times 0.8, I will then have on average 48 volts. And that averaging goes actually through a filter, so that's actually shown here in a simplified form. But you can see here that this is already some sort of a filter due to that inductors, but actually you need maybe an additional filter to make this more smooth. Alright, now we have calculated also the required duty cycle for this situation by chopping the given terminal voltage of 60 volts in order to reduce the shaft speed from 125 radians per second to 100 radians per second. Okay, this concludes this example about a DC series motor in order to calculate the required terminal voltage to reduce the shaft speed, and also by using chopping, in this case in a simplified form given by a switch. If you have any questions about this exercise, please let me know and I will try to answer them as soon as possible. And see you next time and take care.